Hey everyone, welcome to this explainer. Today we're going to challenge one of the most famous facts we all kind of just know about the universe. I mean, if you've ever watched a sci-fi movie, you're probably super familiar with the classic tagline, right? In space, no one can hear you scream. And scientifically speaking, that actually makes perfect sense. We're taught pretty early on that outer space is essentially a giant vacuum, completely empty of the air molecules you'd normally need for sound to travel. So it naturally sets up this foundational idea in our heads that the cosmos is just this vast, completely silent void. But okay, here is where things get really incredibly fascinating. If space is truly a vacuum, how on Earth, or I guess off Earth, did NASA recently release actual recorded audio of a black hole? You've probably even heard it scrolling through the news or social media. It's this incredibly deep, eerie, cosmic humming sound. It honestly feels like a total contradiction of everything we know about basic physics. Like, how can we have audio from a place that literally lacks any physical medium for sound to travel through? Well, to unravel this whole central mystery, we need to take a quick step back and look at the actual science of sound itself. So, let's dive right into this. To solve our little paradox, we first have to ground ourselves in the physics of waves. Broadly speaking, there are two totally distinct types of waves we're dealing with here: mechanical waves and electromagnetic waves. Sound is what we call a longitudinal mechanical wave. What that actually means is that it physically requires a medium, like air, water, or even a solid object, to compress and expand just to move its energy forward. But on the flip side, we have electromagnetic waves, like light or radio waves. These are transverse waves, and they play by an entirely different set of rules when it comes to zipping across the universe. To perfectly illustrate this difference, just take a look at this actual answer from a high school intro physics exam. The student absolutely nails the concept here. They point out that electromagnetic waves are what you'd use to send signals to a rover on Mars, because unlike mechanical waves, electromagnetic ones can travel freely through a vacuum, like outer space. Light, X-rays, radio signals, they don't need air molecules to bump into each other to carry their energy. They just radiate straight through the empty void. Sound waves, on the other hand, being mechanical, are completely trapped if there's no medium to carry them. It's honestly fascinating to see how fundamental this distinction really is. Over on the left, you can see another student noting that for getting a signal to Mars, a mechanical wave just can't travel through a vacuum, because again, it needs that medium. And on the right, the student correctly identifies sound waves as those longitudinal mechanical waves we use to talk here on Earth, and radio waves as the transverse electromagnetic ones we use for cell towers. Without a medium, like the thick atmosphere we have here on Earth, mechanical sound waves simply cannot propagate. In a true vacuum, they are literally dead on arrival. Okay, so knowing all of this, how in the world did NASA get sound from a black hole? Well, get ready for the big twist of our paradox. It turns out, space isn't always a complete vacuum. Sure, the vast stretches between star systems are incredibly empty, but there are exceptions. And the most spectacular exception is a region known as the Perseus Galaxy Cluster. When astronomers actually pointed their instruments at this specific cluster, they realized that the environment surrounding its central black hole was anything but empty. See, the Perseus Galaxy Cluster is absolutely massive, and it is entirely enveloped in this huge, copious amount of incredibly hot gas. This gas cloud surrounds hundreds, maybe even thousands of galaxies within the cluster. And because there's just so much gas packed in there, it actually provides the exact physical medium needed for sound to travel. Since way back in 2003, astronomers have observed that the black hole at the center of this cluster is sending out these immense pressure waves. And these waves are actually causing physical ripples in the cluster's hot gas. So yeah, it is a genuine, literal sound wave traveling through space. But there's a bit of a catch. Even though it's a real sound wave, you couldn't just float out there in a spacesuit and listen to it. Scientists actually calculated that the natural note this black hole is humming is exactly 57 octaves below middle C on a piano keyboard. Just to put that into perspective, that is a frequency drastically lower than anything the human ear can even begin to detect. It's basically a cosmic bass drop that is so unimaginably deep, it literally takes millions of years just for a single sound wave to pass by. So the crucial point here is that scientists couldn't just play the raw audio for us. They had to translate it so our puny human ears could actually process it. To do this, they extracted the sound waves stretching outward from the center and resynthesized the signals. They scaled them up remarkably, somewhere between 144 quadrillion and 288 quadrillion times higher than their original, true frequency. I mean, just look at that massive number. A quadrillion is a 1 followed by 15 zeros. NASA did this incredible scaling work to release the actual audible sounds for their annual Black Hole Week, allowing us to finally hear the genuine ripples of a black hole. But what happens when astronomers want to listen to other parts of the universe? Places where there isn't a massive cloud of gas to carry a mechanical wave. Well, for that, they pivot to a totally fascinating technique called sonification. Sonification is essentially the translation of astronomical data into sound. So when there are absolutely no literal sound waves present at all, scientists take the visual and numerical data collected by telescopes, like light, X-rays, or radio emissions, and they mathematically map that data onto audio tracks. It is a completely different way of processing the universe.
Let's look at a prime example of this. You probably remember the massive black hole in the center of the Messier 87 galaxy, often just called M87. This is a 6.5 billion solar mass absolute monster, famously the first black hole ever imaged by the Event Horizon Telescope back in 2019. But like Perseus, we aren't detecting any physical sound waves rippling through gas here. So how do we hear M87 if it doesn't emit sound waves we can just scale up? The secret lies in combining data from multiple different telescopes and basically assigning them a musical voice.
And this brilliantly illustrates exactly how they pull that off. Scientists systematically translate non-auditory electromagnetic data into music by mapping different wavelengths to specific auditory pitches. It's kind of like a giant cosmic synthesizer. As an image is scanned from left to right, the data is played back to us. Radio waves collected by the ALMA telescope down in Chile are mapped to the lowest tones. Optical light gathered by the Hubble Space Telescope plays the medium tones. And those highly energetic X-rays detected by the Chandra X-ray Observatory trigger the highest tones. So the brightest part of the image, right where that massive 6.5 billion solar mass black hole sits, actually corresponds to the loudest portion of the resulting audio track.
This data-to-sound translation process has become incredibly advanced over the years, and it's being used across a huge variety of cosmic phenomena now. Recently, scientists have even taken the breathtaking, full-color infrared images and data from the brand-new James Webb Space Telescope and sonified them. They've crafted these complex soundscapes for the stunning cosmic cliffs in the Carina Nebula, mapped the contrasting tones of the Southern Ring Nebula, and they've even translated the individual data points in a transmission spectrum of WASP 96b, which is this massive hot gas giant exoplanet. It's pretty wild stuff.
I absolutely love this quote from the team behind the Webb sonifications, because it just perfectly captures the spirit of this whole endeavor. They say, these sonifications are like modern dance or abstract painting. They convert Webb's images and data to a new medium to engage and inspire listeners. It is so vital to remember that these aren't literal sounds being recorded by some microphone floating around in space. Instead, brilliant musicians and scientists have carefully mapped the telescope data into sound, meticulously composing it to accurately represent the scientific details they want us to focus on. It really is this beautiful blend of rigorous science and interpretive art.
But beyond just being an awe-inspiring artistic translation, there is a very practical and honestly vital why behind this entire sonification project. NASA and its partners developed these audio tracks specifically to support blind and low-vision listeners. For decades, the wonder of astronomy has been almost entirely visual, completely reliant on glowing photographs of nebulae and galaxies. But by converting this rich visual data into complex, multi-layered audioscapes, it provides a brand new, fully accessible way for visually impaired individuals to actively experience the data, the scale, and the sheer wonder of the cosmos right alongside everyone else.
So, from literal pressure waves echoing through the gas of the Perseus cluster to the incredibly artistic and accessible sonification of X-rays from M87, we are constantly discovering entirely new ways to process our cosmos. It just goes to show that even in the vacuum of space, there is so much more to experience if we just change how we look, or, in this case, listen to the data. It really makes you wonder, what other hidden senses might we use to understand the stars in the future? How will you explore the universe next? Make sure to subscribe and like this explainer for more, and we'll see you next time.